Alright, so today we're back to learning about some numerical techniques to actually estimate the values of integrals. And sometimes we can't always find them, and sometimes we have to do things by hand because we don't have an antiderivative formula to evaluate our definite integrals. So we're going to look at the midpoint rule, the trapezoidal rule, and Simpson's rule today. The midpoint rule is pretty much what we've already done with Riemann sums, except for we're doing it with our C of i's being the midpoint. So since it's tedious, we're really not going to do too many of these with more than like n being 4, because otherwise just the calculations are too long and drawn out. And the same thing with the other rules, we're only going to do some of these by hand. So this is our familiar formula, so we're actually just approximating it as the sum of these rectangles and not even doing the limit as n approaches infinity today. We'll just be doing some of the simple ones, and then I'll show you how that compares with Simpson's rule and the trapezoidal rule, and you'll see that we get closer and closer to the actual value of the integral. And you might be asking, well, why are we doing this? Well, we'll see some that we just don't have a formula for yet. And later on, we'll go and do some other formulas and some other integration techniques. But right now, there's going to be some that we don't have a rule for that we can actually easily do it with. So here we're just going to do the midpoint rule. So we kind of did something similar to this before, except for we did a lot more involved steps when we did our limit. So here we've got n equals 4. Just like before, we're going to do delta x being b minus a over n. So in this case, we got 1 minus 0 over 4. So my delta x is 1/4. And we're pretty much just going to figure out our numbers. So our subdivisions, our first x would be 0. Our second x would be 1/4 away from that. So we pretty much divide 0 and 1 up into quarters when we do this. So 1/2, 3/4, and then our last one is 1. Now the reason why I'm doing that is those are kind of where that's an even break in all of our intervals between 0 and 1 of that delta x. And then we've got to find our c's that we're evaluating our function at by doing the midpoint of each of these. So C1 is going to be the midpoint of 0 1/4, and that's just 1/8. C2 is going to be the midpoint of 1/4 and 1/2, which is just 3/8. So you do that for all of them. And I'm just going to go ahead and cut to the chase on C3 and C4. So you add the two values. So the last one's 3/4 plus 1 divided by 2, and that gives us 7/8. So when we do this, we're saying that our integral up here is approximately equal to the sum from I equals 1 to n of f at these evaluation points times delta x. So we're saying this is approximately equal to what we're doing. So our integral is going to approximately be our delta x. We can pull that out front, and then we're going to do f at our evaluation point. So f at 1a plus the function at 3/8 So our integral is going to be approximately equal to 1/4 times my function at these 4 points. So this is pretty much what we did before, except now we're making sure we're doing midpoints each time. And we're just going to plug 1/8 in and square it to my function, and then we're going to add the function at 3/8 squared plus 1 Alright, so doing the math, you'll see I've got 1, 2, 3, 4 right there, and I'm going to leave all these as fractions. So 1/8 squared is 1 over 64, 3/8 squared is 9 over 64, 5/8 25 over 64, and 7/8 49 over 64, and then it's plus 4. And we're going to leave this as a fraction. If we add all those up and make 4 into 64ths, we're going to get 1/4 times 340 over 64. And in the book, in the directions for these problems, it says to leave this as a fraction. So we're going to leave this as a fraction. That's 85 over 64. And for future reference, I'm going to go ahead and approximate it just so you can see that we're getting closer to the actual value when we do the actual. In this case, we can compute the definite integral for this function. So I want you to see how we get closer and closer to the actual value. So that was the first example. Now, we've got another rule that I'm not going to go into detail exactly how this works by hand, but instead of using rectangles, this method uses trapezoids to predict the area, so that when you're doing a curve like this, instead of a rectangle, so we don't have that anymore, we have more of a trapezoid that kind of touches a little bit more of the curve, and this one would be another trapezoid. So we get actually closer and closer to the area with this formula. So I want you to notice something. The main thing to note here is that I do b minus a over 2n, so it's a little bit like doing delta x over 2. Some books have it that way. And then you've got the function at the same evaluation points that we started with. We don't have to actually do the division. And notice that each of these in the middle has a 2, so the two endpoints do not have a 2. So when we're doing this, I'm doing the exact same function as before, and we're doing b minus a over 2n, and then we're doing the function. In this case, since n is 4, we're just doing the first 4. So we've got 2 of these x1s, that's 2 of the x2, plus 2 of the x3, plus f at x4. Alright, so we have the same x's from before because we're doing delta x being 1 over 4. So we've got 0, 1/4, 1/2, 3/4, and 1. So now we just have to do our substitution into this formula, and it's not too bad. We do 1 minus 0 over 2 times 4. We do our function at 0, so 0 squared plus 1. We do our function, 2 of our functions at 1/4. I wrote the wrong thing down there. We do 2 of this, 1/4 squared plus 1, plus 2 of 1/4, 1/2 squared plus 1. And then I've got 2 of the 3/4 squared plus 1. And I've got 1 squared plus 1 at the end. Alright, so this first part just becomes 1/8. And then 0 squared is 1, plus 1 is 1, and then I've got 2, 1/4 squared plus 1 is going to be 17/16. And then I've got 2, 1/2 squared plus 1, that ends up being 5/4. I've got 2 3/4 squared plus 1, that's 25/16. And then 1 squared plus 1 is 2. So when we add all these up together, we get 1/8 of 86 over 8, and that equals 86 over 64, which is 43 over 32, and it's approximately, as a decimal, 1.34375. So you can see it's a little bit closer than the other one was. And that leads us to our Simpson's rule, which will be the closest of all. So we're only going to do 4 of these by hand. I want you to notice the pattern of the coefficients. So we start with nothing out here, nothing at the end, and then it goes 4, 2, 4, 2, and keeps repeating that until we get to a 4, and then there's 1. So we've got a very similar idea before with b minus a over 3n, so that's delta x divided by 3. And really, plugging the stuff into the formula is fairly simple, alright? So we're doing the same evaluation points as we had before. So we've got 0, 1/4, 1/2, 3/4, and 1. We got b minus a over 3n. So we do b minus a over 3n. So that's 1 minus 0 over 3 times 4. And then we're going to do, the first one is our function at 0 squared plus 1. The second one is going to have a 4 with it, and we're going to do 1/4 squared plus 1. The next one is going to have a 2 in front of it, and we're going to do 1/2 squared plus 1. The next one is going to be a 4, and we're going to have 3/4 squared plus 1. And then we're going to have our 1 squared plus 1 at the end. Alright, and if we do this, again, 0 squared plus 1 is 1, 4, and 1/4 squared plus 1 is 17/16. So these numbers are just like the last part of the previous problem. And if we add all this up, we end up getting 1/12 of 64 over 4, which equals 16 over 12, which equals 4/3. Now, you might be saying, hey, we had something very similar to that before. We had 1.3 and some change, and this is 1.3 repeating. If you look at the actual absolute, the definite integral, and calculate it out, that's what you're going to get. Now, I'll show you in class how to use a little calculator for the next couple problems so that you don't have to do all this for n equals 10, 20, 40, 50, a big number.